Okay. Thank you, Artur. Thank you for having me. So my talk is going to be about tensor network approaches to simulations of larger superconducting circuits, and this is a hardware-focused talk, but because most people here, I guess, are theorists, I just want to hook you with spin Hamiltonian. So we have the transverse field, the longitudinal field, and the couplings, and here just a general spin with all kinds of two local interactions. And the talk is essentially about just this question about how to efficiently link the implementation to the spin Hamiltonian. And the first part is about how to link the implementation to the spin, and then the second part. And this is actually the novelty, is about the efficiency. And to guide you a little bit through the talk, I have these little icons. So the implementation is the lumped element Hamiltonian, and the spin Hamiltonian is depicted with this couplings. And so we are here with these little icons. We're at the end where we want to arrive. So first, we need to choose a platform. We at Qilimanjaro, we use superconducting circuits, and to implement a single spin can be done by persistent current qubits, for example. And our kind of design at this stage was a flux qubit with 4 junctions. So the boxes with the X are the junctions. Then we have this nodes describing like the degrees of freedom of the circuit, and then a flux through the loop, which is enabling to control the circuit. And this is corresponding to lumped element Hamiltonian, which in general has this shape. So it has a shape, has some kind of charge operators, which acting on these nodes. Then the capacitance matrix, which can bring all the capacitances in the circuit, and then some nonlinear terms from the nonlinear potential of the junctions. And then to understand this in terms of a spin Hamiltonian, we introduce the persistent current basis. So this is a persistent current which can go around clockwise or anti-clockwise. And if we just project the lumped element Hamiltonian to the spaces, we get already like the transverse and longitudinal field. And so this is already like the first part of the Hamiltonian. And then in the second part, we want to also introduce couplings. So we need to introduce coupled circuits, which is done by like using 2 of these flux qubits, which I introduced before, and also like a tunable coupler in the middle. So we have all these junctions, 2 qubits, and or like 5 controls to control this, and 6 nodes, and which describe like the size of the system basically. And if we do the same thing, the lumped element Hamiltonian has again exactly the same shape. It's just much longer. It's very tedious to derive. It's going to take you maybe 1 day to do it, and it's going to get like 30 terms, but essentially it's the shape again. And to understand this in terms of spin Hamiltonian is now much more difficult, because actually like the higher energy levels mediate decoupling. So mixed states will become like the new lower energy Hamiltonian. So I cannot just project into the simple. There's no simple projection in the low energy subspace. So there is this standard numerical procedure, which is basically deriving the lumped element Hamiltonian. You do exact diagonalization. You do this Schrieffer-Wolff transformation, which allows you to get the low energy subspace, taking into account the higher energy levels. And you get the effective Hamiltonian describing the lower subspace, and then you can just expand into Pauli coefficient and get the spin Hamiltonian. And so we're here in the scheme. Again, we have the lumped element Hamiltonian already. Now we want to get the eigenvalues. So we do exact diagonalization. This Hamiltonian needs to be represented in some numerical way, because we use like discretized charges, which in principle can be like infinitely many charges on one node. We need to truncate it at some point, but this truncation shouldn't like influence the result. So should like the eigenvalues should converge, but in this case they're not quite converging. And the problem here is that they're not converging even on a very powerful computer. So here I plot the number of elements in this matrix representation, the number of nodes, which correspond to the size of the system, and also the memory required to represent this matrix here, like assuming like full matrices. So if I run the previous problem on 1 terabyte of RAM, I get only to the orange star, which is a bit above this 1 terabyte because they're sparse matrices. And so this is like a pretty modest sized circuit, and it's already not like able to simulate even on pretty big resources. So this exponential scaling of this representation is really not efficient. So we need to come up with another scheme. So we look at our procedure again, and I just introduced that we face this computational bottleneck. We cannot do this exact organization for this large matrices, and we want to also capture strong coupling effects, so we cannot do like the common approximations. So we need to do something around here. So we need to get some more efficient representation and also some more efficient procedures here. And with this I come to our method, which is here I ask the question, what can this representation be? And we ask ourselves, what about tensor networks? They're pretty fashionable topic. So I just have one slide to give you a little bit of intuition about them. So you have either like a generic entangled state, which is fully entangled and interesting, but has like exponential scaling with the number of parameters. It was already mentioned before today. Or you have a product state, which has like very efficient scaling in the implementation, but is not interesting, is not capturing like the strong coupling. And then like for many years already, many quantum physics people worked out this scheme of tensor networks, which is basically a product of simple objects. So we have like some local structure, and we can introduce some entanglement, and also very interesting, we can tune this degree of entanglement to find a good representation which is efficient. And then we modify the procedure. So we use in this context the matrix product operator, which is just some kind of tensor network, which we construct in a very simple way, which I'm going to show in the next slide. And then we solve this tensor network with the most common procedure to solve this kind of tensor network, which is called density matrix renormalization group algorithm. And then you can apply the Schrieffer-Wolff transformation. We also put this into the tensor network framework to stay consistent. So I give like a little bit more details on this. First, about the representation. So we have this kind of Hamiltonian which correspond to the circuits I showed before, and then you do derived like the matrix representation, which is exactly already the same what you have to do if you don't do the tensor network way. And this is basically writing these charge operators in terms of like this kind of counting operators of the charges on the nodes, and then you can basically find a matrix representation which is very close to the lumped element circuit. And then we basically spent some time to find a manual way to implement this, which was another tedious stuff already after like this derivation, but actually we found a better way, which is using a software package which is called a tensor, and there you can just sum about all local operators, and this means you can find a very efficient representation with a like pretty straightforward way to formulate it. So you'd only need the lambda element Hamiltonian, and then this is very close to formulate the MPO. And then I also want to talk a bit about like the next step about the eigenvalues, eigenvectors. So we need to solve this MPO now to get these. So the most common way is to do the DMRG, which I give you a little bit of intuition, is an iterative process to sweep through the tensor networks and then always cutting away the least relevant degrees of freedom, so you can get like a very low ranked tensor approximation, often, not always, and then you have a like efficient representation, and then this can be solved easily. And then we also, because we really want to push to as large as possible circuit, so we use also HPC computing with GPUs, and then also large-scale parallel computing on a supercomputer here and on Amazon Web Services. And then I come to the preliminary results. So they're preliminary because I would like to get more, like a bit more conclusions from them. They're pretty recent. So and they're so far only reached the eigenvalues, but this has shown to be like the most important bottleneck we want to solve. So first sanity check in the regime where we can still do exact diagonalization is just a single persistent current qubit, and we sweep one of the external flux and match exactly, so the method seems to be working. And then we also do two coupled flux qubits, and here we do a 1D sweep, and we can sweep one, for example, in this case, just one of the qubit fluxes, and we can see this whole energy because we have the Schrieffer not ready yet, and then we can see this expected periodic structure. So this is kind of a preliminary proof of concept that we can calculate something which was impossible to calculate with the previous methods. And then we can also do 2D sweeps, which are basically sweeping this, the flux into this loop, which is modifying the size of this junction. And then we can sweep, again, the Zs. And then we can see the whole energy. And then this is also basically the expected structure, more or less. And then I can adjust the color scale that we can see like the periodicity in the two ranges. And we're also working on Fluxonium. We start working on Fluxonium. It's quite different problem because we have like a few less modes in this case they're called. So in this exponential scaling is quite a big difference, but we have like much larger dimension of the nodes, or in terms of tensor networks of like site dimensions. And so if we want to do exact diagonalization of like two coupled Fluxonia with a tunable coupler, we can reach with 1 terabyte like about this orange star again. And this is working but slow. And in yesterday's talk by Andrea, you've seen like some results on exactly the same system where we employ the hierarchical diagonalization, which is really efficient, so we can calculate one data point in 1 second on the laptop. But it's less adaptive because you need to leave some choices on the system, so instead of like our scheme, which is able to adapt to the structure of the system. And yeah, we are currently studying if we can see something more in the tensor network scheme compared to this hierarchical diagonalization. And we have done the first step, so we can calculate, again, the sanity check of the single fluxonium, and also we match the result of the hierarchical diagonalization for the two tunable coupler. And so I come to the outlook and conclusion. So on the outlook, we still want to fulfill the promise to get to the effective Hamiltonian and to the coupling terms. So we want to employ this Schrieffer-Wolff transformation, which is transforming into this low-energy subspace, taking into account the latter levels. And yeah, we have this implemented, but I cannot show conclusive results on this yet. And we hope we can see something which we couldn't see before, which we think is quite possible due to this previous work by Maria, where she studied a similar system. And then we go to, we want to scale to more qubits, especially fluxonia. And then we want to also make a conclusive benchmark on the accuracy, so to really show that the accuracy is higher. From now, we claim this because, from the approach, it seems reasonable, but yeah, we want to also show this in our results. And then also on the computational performance to also understand which kind of systems we can reach. And yeah, for now I explained this tensor network perspective only as a kind of numerical procedure, but it's actually a different kind of understanding the system. So we also want to use this perspective to understand the system in terms of entanglement between the sides and this kind of stuff. So the conclusion of my talk is basically that we built a scalable framework which we implemented and currently validated to do all this, so to do larger simulations for strong coupling circuits. And with the previous result, I can show that we can reach systems which we couldn't simulate before. And then, yeah, next is also to study actually the couplings as promised and then scale to more qubits. So that's it. I'm happy to answer your question.
Okay, questions? Questions? Okay, Matthias. Let's go.
You'll live longer for it. So. Yeah, so you showed the plot where you showed the number of matrix element and you also and how they scale and also how much memory you used for it, right? Mm-hmm. Because I think you said it's like a sparse matrix. Do you know roughly how many elements are zero in those matrices?
I mean, I'm not sure. I mean, we can go significantly above. I mean, this is exponential scale, so that we can encode this. This is kind of the same distance between the 1 terabyte and the point we reach, also for the flux qubit. So there's some substantial part which is sparse, but I think it's also very dependent on the circuit, especially if we have capacitance terms between all the nodes, and how you design your circuit and how accurate you want to.
Okay, more questions? Sorry.
So I was wondering, were you simulating just 1D geometry using tensor network or other geometries as well?
So for now we only use MPOs, but
okay.
Maybe at some point, depending on the circuits we want to simulate, so we are open to also use other approaches.
And what is the system size you were doing DMRG on?
So I mean, this is quite of a curious setting for tensor networks people. So we have, in this case, only 4 sites modes correspond to sites in tensor networks language, but you have 50 dimensions of like the local sites. And this, like for the persistent current, this was 6 sites and 21 dimension of the local basis.
Okay, thank you.
Okay, more questions? We have time. I have a question. So this clearly should fail when you go to the large limit, right?
Yes.
Why should it fail? What can you see some underlying reason because of the coupling between these modes?
I mean, depends on like the longer range interactions. I guess if you have like only local interaction, then maybe it can scale quite well. If you want to have like longer range interaction, and they all should be strong, then basically the advantage of the tensor network will also not be so large because there are not so many like degrees of freedom you can cut away basically.
Okay, thank you. Any question more for the session? Okay, let's thank the speakers of the session, Chris.